This is how electromagnetic waves move through space. Electromagnetic waves are waves like light. Keep in mind that there's light we can't see. So when we look at the electromagnetic spectrum, it'll show us a thin sliver of the visible light that lets us see all the stuff we see with our eyes, and a lot of invisible light on both sides. The thing to understand about this is that we see a very small sliver of the available light that exists. We call that visible light, which are basically the colors. We don't see UV light from the sun, but we wear sunscreen for it, and we don't see infrared light or microwaves or radio waves, which are used for like Wi-Fi and communications. We don't see X-rays or gamma rays. Those are all types of light that we don't see, or invisible types of light. Now, there are some big ideas here that you should understand. Notice how there are different wavelengths, and therefore there are different frequencies. But no matter what, all of those light forms, so all of those lights, they all travel at the speed of light. And that is a fixed value, which we call a constant. So regardless of the wavelength and regardless of the frequency, all of these forms of light travel at c. The variable for wavelength is lambda. And the variable for frequency is oftentimes f or nu. Nu is a Greek letter. It kind of looks like a V, like a really cursive V, but it's not a V. So I'm going to stick to F because it doesn't look like a V. And that's also pretty commonly used. Wavelength and frequency. What are their units? Well, first we got to think about how are they even connected? If we say that no matter the wavelength and no matter the frequency, they're gonna go at the same speed, which is the speed of light, that means that there's got to be some kind of mathematical connection between wavelength and frequency. And there is. It is c. So here's the equation that connects them. C, the speed of light, is equal to lambda, the wavelength, times frequency. If we check the units, we'll see that they make sense. The speed of light is measured in meters per second, wavelength is measured in meters, and frequency is measured in per seconds, or inverse seconds. But that's kind of clunky to say, so we'll just call it hertz, because hertz is the unit that you'll oftentimes see after a frequency. Do you recognize this relationship? We have a constant. We know that the speed of light is not going to change as long if the wavelength and the frequency change. So that means that if wavelength is high, frequency is low. And if wavelength is low or small, frequency is high. Let's see how that relates to the electromagnetic spectrum. Radio waves have the longest wavelengths, so they have the lowest frequency. And then gamma rays have the smallest wavelengths, so they have the highest frequency. You may be familiar with the fact that this is an inverse relationship. So we're going to write that here because that's an important thing to know. When you have two variables on the same side of the equal sign and they're the product of two things, so like we have wavelength times frequency, we know that one can go up or down and the other will go the opposite direction. That's what we mean by inverse, because C is fixed. I'll tell you now that gamma rays have a lot of energy. They're like what's created when stars die. So what about energy? We don't see energy in our equation here, but energy is certainly something that we would be interested in when it comes to electromagnetic radiation or electromagnetic waves. Energy is denoted by the letter E, and there is an equation that relates them. The equation here, E for energy, is equal to h, Planck's constant, we'll talk about that, times frequency. This equation relates energy and frequency, but what if we want to know the relationship between energy and wavelength? What we can do is we can actually take this first equation and rearrange it. I took this equation and I rearranged it to solve for frequency because we do have frequency in the energy equation. So we can actually do a substitution. Since F is equal to C over lambda, we can put C over lambda where F is in that equation. That gives us E equals hc over lambda, which I can also rewrite like this. And now we have an equation that relates energy and wavelength. Now let's think about all 5 parts. The speed of light, is it a constant or a variable? The speed of light is a constant. Wavelength, though, will be a variable because it can change. So can frequency, and of course, energy. But Planck's constant, as the name implies, is a constant. So if it's a constant, what is that fixed value? The speed of light, so all light, travels at a speed of 3.00 times 10 to the 8th, so that's fast, meters per second, which you know you can write as a meter times a second to the -1 if you wanted to. And then wavelength does not have a fixed value, but it does have the units of just meters. Frequency has the unit of an inverse second, which can be written this way or this way, but no matter what, it is basically just a hertz. And then we also have energy, which has the units of joules. And finally, we have Planck's constant. Planck's constant has a fixed value as well, because it's a constant. It's 6.626 times 10 to the negative 34 joule seconds. That's a weird unit. Joule seconds? Let's explore where that comes from. If we take the equation, the original E equals hf equation, and we solve it algebraically for h, we'll get E, or h equals E over f. Now, if we examine the units, we know that the units for energy are joules, and the units for frequency are an inverse second, which is an s to the negative 1, which we also, again, write as 1 over s. So, if we take that equation for Planck's constant, h, and we rearrange it just a little bit, we'll get E equals h times f to the negative 1. Now, if we take the units, what we're going to have is a joule, and then frequency we know is s to the negative 1, but we also invert it again, we just bring it right back upstairs, and it's s. And that explains why Planck's constant has units of joule seconds. So when it comes to the electromagnetic waves, you're going to use these three equations, and just realize that this last equation is really just an algebraic combination of the first two.